Welcome back. This is a video on the Rayleigh-Ritz approach to bending. There will be no axial strain energy in this problem. We covered the axial one alone. The similarity to the axial problem arises from this, which is an assumed displacement function. This is not truth with a capital T. It is made up of a constant, which we don't know, so therefore it's really a variable, and an admissible function. I had a question about how could we differentiate with respect to a constant. Well, I don't know this number. This thing is the thing that wiggles. This one wiggles. The admissible functions mean that they must satisfy essential boundary conditions as before. The work is, not the works, but the work is a bit confusing. I think the book is not super clear on it. I hope to be perfectly clear about it, and I gave you some hints. A low-level interpretation is this, that if the load is 0 and it ramps up slowly to some final load, then we have to have the factor 1/2 because that shape is a triangle, the area under that curve. If the load is on the body and another load is applied to it, as in the unit load method or in Castigliano, then the shape is a rectangle and there's no 1/2. Here is the major hint. If the load is in the same direction as the displacement, use a minus sign, and if it's in the opposite direction of the positive displacement, then use the positive sign. What this really is this is potential energy here, and the potential energy increases if you are in opposite directions here, and the potential energy decreases, if you are applying load in the same direction. So here's some examples here. We have 3 major cases for our beams. We have a distributed load. Of course, this function must be known. It cannot be an unknown or a probabilistic function. And it pushes the beam to some v, and the product of q times v integrated over the length is the work, no 1/2. So in my notes here, I purposely put the 1/2 in there so that you would remember that there is no 1/2. I took it out here. Ignore the 1/2 during du is equal to dw, which would mean q is equal to 0. Here we're going to set q to be minimum, not 0. Notice I have q going up here and v going up, so that would be this case here of u minus w, because they match. The second case would be a concentrated load. Here's the direction of positive displacement. Here's the load. The only trick, or if you want to call it a trick, is that this is at the work is uses P times V at x equals xp. So that's what that line means here, at x equals xp. And xp is the distance to the load. Your author has this on page 469. It's equation 6.12-2. And then the third case is that of a concentrated moment. The work is moment times theta. If there were something like a distributed moment, we would integrate. But here we have discrete concentrated moment. And again, this is at x equals xm, where the moment is applied. And once again, we have an equation for that, 6.11-4. For the strain energy, now this is a little tricky. I have a second version of this for you. We've seen this in the Castigliano. I'll provide this for you in any exam situation, but let's be aware that there's 2 formats of that. Okay, so the two major problems are the sign here, as I said, and the 1/2. Okay, and if you have that, I think you got it. The rest of it is very, very prescriptive. In other words, there are steps that you just do. Students really like this method. I think it's quite brilliant. Of course, Rayleigh was a genius, so I think you're going to like it. And it's pretty intuitive, I think. And as I said in class, it leads exactly to the finite element method. So here we have the beast again, our cantilever load subjected to a single point load. And here we assume some displacement, which is a polynomial, and these are constants. So this is a constant, and this is constant. The A's, right? Etc., etc. What you'll find in homework as you explore this is that you could add more. You could add a4 to the x to the fourth, etc., etc. But unneeded terms will zero out. Unneeded, I'm not sure how to spell that. Unneeded terms will zero out. So that'll be a fun thing to explore later on. In this example here, I gave you 4 constants. Do you know any of them? I think the answer is yes. As the beam deforms, we have to have a 0 displacement here, which means that this has to be 0 because at x equals 0, we cannot have a non-zero v. And then dv dx is the slope. And if this at x equals 0, the slope cannot be a 1 when we differentiate that, so that's out too. So we have a 0 is equal to 0 and a 1 is equal to 0, just by kind of engineering insights. Let's calculate the strain energy due to bending. A couple of things to think about when you're doing this is we could start with equation 6.11-4, which is our capital UB is 1/2 0 to L of EI, and then it's d squared V dx squared, the second derivative. We square that and it's dx. And I think you could see where this is headed here. I have V, that's assumed, so I have to find dv dx, and then I have to find dv dx, the second derivative of dv dx, so dv dx squared. There's another format here that I think is worth mentioning. I'll probably give you a homework problem on this, and it'll pop up at some point. Your favorite differential equation from the undergraduate curriculum, probably the only one that you remember, is m is equal to ei d squared v dx squared. And I just happen to have a d squared v dx squared here. So what's happening here is I have ub is equal to 1/2 integral of 0 to L of EI times m over EI from what I just showed you squared. And what happens is that gives me m squared over EI. And that will be an alternate format of our bending strain energy. So in our example here, we had a2 x squared plus a3x cubed, so maybe let's rewrite that again. V is equal to a2 x squared plus a3x cubed. So the first derivative is trivial. dv dx is 2a2x plus 3a3x squared. And then our second derivative is also trivial, dv dx squared. I have 2a2 plus 6a3. The work is this second case that I showed you here. of the three possible cases. It's this one here where we have a concentrated load. And remember, I have to express the work at this particular location where the load is applied. So P at XP. P times V, where V is evaluated at XP. So at that particular point here, and that is XP is equal to L for us here in this example here. So here XP is equal to L. So the work is P times this expression times A2L squared plus A3L cubed. The next step is the strain energy, U. So this is this one I just did was work. This is strain energy. And I'll use that first format that we just established here, not the second one. I'll call this the second format. This is the first format here. And I'll use this because I happen to have this d squared v dx squared right in front of me, so I may as well just use it. So here it is. U is equal to, that's U bending. Of course, we have a U axial, but we're not doing axial in this problem. U bending is 1/2 EI, integral of 0 to L, of the second derivative of V with respect to X. And I square that, and then I integrate it. That looks like a fancy schmancy equation, but it's really not sophisticated at all. It's 1/2. I could pull out the EI here, and I have the integral from 0 to L of 2A2 plus 6A3, which you just see right here, and 2A2 plus 6A3. You could expand this out. It's super easy, and then integrate it, or you could ask your robot to do it. And here we have U is equal to EIL times 2A squared plus 6A2A3L plus 6A3L squared L squared. So far so good. Next, set up Q. So the first question, and this is the stumbling block. Remember I said Q is equal to capital U plus or minus W. So is it plus or is it minus in our problem? You have to be super careful when looking at the directions here. And for us, this is opposites. So we have V going up and P going down. So which one do we use? Which one do we use? The opposite. It's U plus W. We use this one. So Q is equal to U plus W. I'm sure you'll screw this up at some point, but I think it'll be obvious for some problems, but for other problems you won't know what the heck you did. So, and I don't think the book is super duper clear on this. So let's say U plus W. And now it's quite easy here. I just have U right there. So EIL 2A squared plus 6A2A3L plus 6A3 squared L squared plus, this is where you can screw it up, and the W, which we just figured out here, the work. P A2L squared plus A3L cubed. Oh, wait. Oh, sorry, I have an L squared out here. So P, no mistakes here. P times A2 L squared plus, I think I had a mistake in here. P, here, I lost a parenthesis here, sorry. So it's P times the displacement at L, okay? All right, so P times L squared times A2 plus A3L. So we have an L cubed, and an L squared. Whew. Okay, now what? This is slightly different than Castigliano, where Q is equal to 0. Now we're minimizing it. And what are we minimizing it with respect to? With Castigliano, we minimized it with respect to that fictitious load if you need to find the displacement at a particular point where there is no load. Here we're minimizing the energy associated with wiggles in these constants. And I love this idea of this perturbation. That's called a perturbation. And it's just like it is in English. You know, if somebody just kind of perturbs you, they don't anger you, they perturb you. They're just little wiggles, right? How many equations do we have? 1 or 2? Well, how many variables do we have here? We have this one and we have this one. So they are constants, but I don't know what those constants are, so they are variables. So I'm going to have 2 equations, and they will be with respect to A2 and with respect to A3. And the reason why students really like this is at this point it's kind of robotic. The differentials and the integrals are super easy because everything's a polynomial. So let's just march through it here. Equation 1, partial Q with respect to A2 is equal to 0. And then equation 2, partial Q with respect to A3 is equal to 0. If we were in class together, I would actually have you do this and I'd walk around here, but it's not, you know, tough at all. This is Q, so just differentiate that with respect to A2 once, and then differentiate that Q with respect to A3, and those are your 2 equations. So our first equation is, this is number 1. We have 0 is equal to 4 EI L A2 plus 6 EI. And you could check this. You might want to stop the video and just kind of check that you could do this yourself. A3 plus PL squared. And then number 2, 0 is equal to, sorry, that was a little sloppy, 6 EI L squared A2. And the units work out, you'll see in a second here, plus 12 EI L cubed A3 plus PL cubed. And that's why the units work out, because I have a PL cubed in equation 2 and a PL squared in equation 1. At this point, you can solve this by hand. And I would like you to solve this by hand. Give it a try. Stop the video and see if you could do this. You could certainly do it by the robot. 2 by 2 you should be able to do by hand. Even a 3 by 3 you should be able to do by hand. That's kind of mean though. That's tedious. But a 2 by 2 isn't so bad. I kind of gave the barn away by showing you A2 and A3 here. But A2 is minus PL over 2EI. And A3 is P over 6EI. So V is known. You pop this A2 into here and this A3 into here. And we have an expression for V for our beast. And that means V at any x, V at any x. Now it's not a function of y, but it's a function of x. So it's not super robust, but it's an approximate method. And what I'm going to ask you to do for homework is check how good is this approximate method. And I'd like you to check it at a few spots. I'll walk you through that in a second. So let's go back to this. How does our thing that we just found compare to theory? In other words, how does this equation really work with theoretical answers? And you could certainly ask Siri, or you could open up a steel manual or a timber manual. And the answer is that it works exactly, which is kind of remarkable, right? That you just have this polynomial that Sir Rayleigh did and Ritz sort of reinvented later. It's just a polynomial. Where was it here? And they're always going to be super simple like this. They're going to just be super simple polynomials. No hyperbolic cosines or anything like that. Just stuff like this. And it's so cool that it works perfectly, right? Okay, so for homework, we have something slightly more complicated, but the feeling is exactly the same. So we have a prismatic beam, which means E and A are constant. We have a uniformly distributed load instead of a point load. So make sure you go to the right case when you're doing your work. And I gave that to you. That'll be this one for homework. Check your signs. Make sure you know which way, is it U plus W or U minus W? Okay. And then finally, here is our same expression that we just used before. A0 plus A1x plus A2x cubed plus A3x cubed. A2x squared plus A3x cubed. What I want you to do at the end of the day is calculate this v as a function of x, and I want you to check it at 2 points. The first point would be right here at the tip. Good, or ugly. Those are your 3 choices. And then I'd like you to do it right here. Good, or ugly. Steps are exactly the same. You know this one and you know this one. You find this, A2, find this, A3. Later, I think we'll add a few more terms if we have a chance, but let's do this for homework, and I'd like that due on Monday, December 2nd, when we come back from the holiday. I'll be around. If you have questions, I got a lot to do, so I'll be in the office. I will be with Familia. So what I'd like you to do is check at x equals L over 2, and then give me like sort of an agreement. In other words, if you're like 93% or above of theory here, you know, give Lord Rayleigh an A. If you're at 85% of theory here, you know, he gets a B or whatever, okay? But it's Lord Rayleigh, so I'm sure he's going to be okay. All right, I think that's it. Hopefully this was helpful and fun.